In this video, we will go over the Tesseract OCR engine. Tesseract actually means a cube in 4 dimensions, and it is just a fancy name, nothing to do with optical character recognition as such. And since I did not have or cannot show you a cube in 4 dimensions, here are some ice cubes. Well, OCR, or optical character recognition, is the problem of recognizing text inside an image. So you have an image that contains some text like this, and you want to get that text out in ASCII or Unicode format. So that's the general problem. And the reason it is called optical character recognition is that earlier they used to have these optical sensors that you would go and put on top of text, just like in this video, and it would recognize the text. So this video has been taken from Wikipedia, but that explains the origin of the term optical character recognition. You have this optical device that goes character by character and does the recognition, as shown here. Tesseract was started in the year 1984 by a PhD student who was sponsored by HP. And the development continued until 1988, and it became an important project in HP, where HP Labs and HP Scanner division joined hands to make this a project. But things did not go very well after that. The scanner project was cancelled in 1990, and in 1994, HP Labs also cancelled this product. However, this was a very good product. It was actually one of the best OCR engines of its time, and still is a very good OCR engine. This project basically gathered dust for about 10 years until in 2005, HP open sourced the project. And after that, things took off. In 2006, Google funded the project, and it took the project under its wings, and Ray Smith is back at Google working on Tesseract. Now, this became very popular after 2006. By 2010, they also had a layout analysis engine, and they had support for about 60 languages. Now, page layout analysis was not part of Tesseract in the beginning because HP had its own page layout analysis software, and Tesseract assumed that you have analyzed the page and found bounding boxes around text, which it could do OCR on. So in 2010, the layout analysis was added, and it became a full-fledged OCR engine. And things have moved a lot since then, especially with deep learning. The accuracy that we get these days is completely mind-boggling. It's very, very accurate these days. And therefore, to keep up with the times, Tesseract has also evolved, and we have a deep learning based LSTM engine now. You can also use the traditional engines, and sometimes they work very well. And the deep learning based recognition engine also works very well, and it's constantly evolving. So the new versions will always be better than the old ones. And these are learning based models, so they get much better when more data is added to the system. So we expect Tesseract to get better and better. And basically, if you consider the entire package of document layout analysis and all the language support, I think it is the best out there. In our consulting business, we have used Tesseract in many applications, but we have also used other deep learning based solutions. But whenever you want to analyze the entire document and not just pieces of the document, Tesseract is the best option out there because it becomes very complicated to write everything from scratch. So it is good to use Tesseract because it gives you a document page analysis as well as the OCR on top of it. Plus, the language support is just incredible. Before we understand the OCR pipeline for Tesseract, let's understand a little bit about text and fonts so that when we refer to things, we understand what we are talking about in the pipeline. So this is some regular text in some font. There are a few important things in this font. This line here, the red line, is called the baseline. It essentially connects the lower end of all the characters except for the ones that extend to the bottom. Then we have the mean line, which is the top of the character. The distance between the mean line and the baseline is called the X height. And there are two other lines like the accent line and the descent line, which are also important. But the more important lines are basically the baseline, the mean line, and the X height. So the other thing we want to understand about fonts are fixed versus proportional fonts. This is an example of fixed font, which says monospace. You can see that every letter or character occupies the exact same space. So these things are fixed spaced fonts. And it is very easy to segment this font because we know that once we have figured out a word, we can easily segment by knowing that it is a fixed sized font. But things get very tricky when we have proportional fonts like this one. You can see that R occupies a much smaller space compared to P. In the fixed fonts, it did not matter. Capital letters versus lowercase, they all occupied the exact same space. But in case of proportional fonts, they occupy different spaces like you see here. And that produces a challenge because the traditional version of Tesseract actually does character analysis. It first tries to segment the character and then classify the character. So here's what the pipeline looks like. When you get a document, the first thing is adaptive thresholding. And we'll see an example in just a bit what this looks like. The goal is to convert the grayscale image to a binary image where the font is dark and the background is white. Tesseract, because of the way it is implemented, also works really well even when the background is dark and the font is white, which used to be a challenge for early versions of OCR engines. But the way the features that Tesseract uses ensures that black on white text and white on black text, they produce the same kinds of features. So Tesseract does very well on both cases. So after you have done adaptive thresholding, you get an image which is clean. And here's an example of adaptive thresholding. So you can see that we had an image, there was some shading here, and it was not looking very good. After adaptive thresholding, we get a nice looking binary image. So that's the goal of adaptive thresholding. The second step in the Tesseract pipeline is the page layout analysis. And this basically means that we are looking at this entire document and then breaking it into segments. So it creates these bounding boxes around regions of text. And these bounding boxes are not necessarily around words. Usually it is around paragraphs and things like that. So that's what the page layout analysis does. Once the layout has been analyzed, it goes into the word recognizer. And there are two passes on the word recognizer. And the reason is that when we make the first pass over the document, they have an adaptive learning mechanism which makes it better as it learns more and more from the top to the bottom. So the accuracy is better when we are at the bottom of the document versus the top of the document. So we actually go and do a second pass on the document, which uses all the information, all the learning towards the end of the document. It uses it again to recognize the words which did not give high confidence. And that is why we have two passes of recognition. Not only that, there are fixes that you can make once you have recognized words. For example, whatever height you had estimated for the character, you can go and fix that. You can fix the space between characters. You can also do bigram analysis to fix some errors. So what is bigram analysis? For example, you have recognized two characters side by side. One is T followed by N. Now we know that it is very unlikely that T would be followed by N. Most likely that next character is H. So you can look at the probabilities and fix, especially if you also see that the next character is E, you can say that this word is THE and not TNE. So those kinds of analysis is also done in Tesseract to fix after the word recognition is done. But it's not really a pipeline. Tesseract does many things in a cycle. So it may do page layout analysis, followed by some fuzzy space fix, followed by some recognition, and then output the text. So there are many cycles that happen, and this could be another cycle. After going through this process, they do an X height fix. And once they have fixed the X height, they want to go and recognize the characters again because, it improves accuracy and things like that. So there are many cycles in the code between these various phases as well. Now, where does the LSTM line recognizer fit in? So when deep learning was introduced, this LSTM recognizer was introduced in Tesseract 4.0. I believe it was less than a year back. And this basically does line recognition. The page layout analysis component passes the bounding boxes to the line recognizer, and LSTM recognizes the line using deep learning in one shot. It doesn't go character by character. It simply recognizes the entire line. And if the confidence is high, in that case, the text is output. If the confidence is not high, then traditional methods are used. So it falls back onto traditional methods and tries to recognize character by character. Now, in traditional methods, you may be wondering what kind of word recognition is used. So it's very, very traditional computer vision based, where they do blob analysis. They try to figure out each character and then figure out each word. And they do all kinds of fixing. For example, they first find the line. And here you can see the line that they recognize is that dark line. But the pages may actually be curved. So they do some analysis, very low level vision analysis on these blobs to fit a curved baseline. So this blue line that you see is actually not a straight line. It is slightly curved. They use some kind of spline for it. And you can see these lines, the black, blue, purple, and the cyan lines, they are all parallel to each other and curved. And they are not parallel to the black line on the top. So this kind of curve analysis allows them to make even better prediction. So they find lines, they analyze the curvature of the page, and you can imagine that the curvature could be much more when you're trying to do text analysis on a scanned book. The middle of the book, when it bends, it can produce all kinds of curvature. So Tesseract is able to handle some of that. So they find the lines, and they also find curved lines. Once they do that, they try to find the characters in each word. And the first thing they do is figure out whether the text is fixed fonts or not. And if the font is fixed, which is not very often these days, but if the font is of fixed type, in that case, they can simply do a trivial segmentation and draw lines at equal intervals and segment out each character and then pass these characters to the character recognition engine, which we will come to in a little bit. However, in real life, most of the text is proportional text, and it has all kinds of problems. You can see that there are no bounding boxes which separate this F and this I. These bounding boxes are overlapping. Even this two Fs, they are not separated by a bounding box. Because of this slant, what happens is the top of the F is actually beyond the bounding box, which would have covered here, the next F. And not only that, the distance between two characters can also vary widely. So for example, the distance between these two ones is very different than the distance between these two Fs, which is almost 0. So even though we can see the space here, the bounding box distance is 0. Now, Tesseract solves most of these problems by measuring the gap in this limited range. So they figure out what is the gap here in this range between the baseline and the mean line. And based on that analysis, they can say that, okay, this is a different blob than that blob. They don't use bounding boxes. In this case, they use blob analysis, and that helps them separate the characters. Now, not only that, sometimes even with these methods, it's not possible to get a perfect chopping of the words. You cannot chop the word into characters perfectly. And when that happens, they combine recognition with character segmentation. So they go back and forth between recognition and segmentation. For example, this word that you see, it says morning, And when the segmentation is wrong, it comes out to be mom. And then they create another segmentation, and you can see that it's still wrong. And they do this iteratively, and finally you can see that the segmentation is correct and this mountain word is returned. So this may look like a lot of, handcrafted engineering, but that is how things had worked. And it's surprising how well Tesseract works and what needs to be done. This is a lot of engineering work, but what needed to be done at that time to make things work. These days, we don't do this kind of engineering. If we want to recognize a word, we basically train LSTM network to recognize the word in one shot. And that is why some of these methods are being replaced by LSTM. But I just wanted to show you the engineering that went on before deep learning was available, and they still made it work. It was very accurate. When it is a common font, it was more accurate than 99.5%. So they did very well, even with this kind of handcrafted engineering. Now, once we have separated the characters, they needed to be classified. So as we know that we need some kind of feature to classify a character. So the features that they had learned were these lines, which are shown using these solid lines. Those are the features they learned. So they say that if you have an O, then the O should have these kinds of lines, and then it should have another set of lines in the interior. But during recognition, they did not need these lines to be precise. They broke the lines into very small segments, and then they simply checked whether they followed this pattern or not. So very simple ideas, but it is all engineering. There's a lot of work that goes into this handcrafted features. And we are really fortunate because we are in this era where deep learning takes care of learning the features all by itself. And that's a new kind of idea that has emerged in the last 10 years, really. So before that, we had to do all this handcrafted feature engineering, which was very, very difficult. But anyways, this kind of character classification is still done in Tesseract if you use the old version of Tesseract, or if you don't use an LSTM model. Now, surprisingly, this actually works very well even when the character is broken. So you can see here that the O is broken and we see these two segments, but when the template is applied to it, most of the template still matches with this O, and this O is correctly recognized. So that is it in the pipeline. I hope that you understood the various parts of the pipeline. We did not go over how they fix the X height or the fuzzy space, etc. But these are all based on some heuristics. So you will have to look at the code to understand how these fixes are made. But the good news is that most of it is not important. If you're interested, you can go over how LSTM works. Unfortunately, it is beyond the scope of this particular course. But if you're interested, read up on LSTM for text recognition, and that will teach you a lot. That is all we wanted to cover in this video. Have fun with Tesseract. There's a lot you can do once you know how to use it correctly. Thank you.